First of all, it's a pleasure for me to be talking to so many people online. In fact, it's a very impressive figure of some 2,500 and more. So I realize that not many people are experts in this field. So I'll be talking something in a very fundamental way, as the title itself goes. And things will be very simple, not a single equation in my presentation. And I like to really start from the basics. At the same time, I think I'm going to share my presentation here. The topic is fundamentals of satellite meteorology, and this is the first first of the, I think about a dozen lectures that have been planned in the next 5 days. It's going to be a simple lecture, but it's a rather long lecture. I think an hour or so, or slightly more, and we'll have a little time for discussion afterwards. So what I will do is to give a brief idea of what I'm going to speak. There are 6 points on this slide. We'll start with a little bit of history. It's always good to start with a little bit of history when you're looking at something for the first time. And we'll end also by discussing what the future holds. In between these two things, there are 4 bullets on this slide. Satellite images and their interpretation. We see satellite images on TV, in newspapers, on websites, and so on. But we also use a lot of satellite data per se and apply them in various fields. So the second thing to know will be what we do with the data. We are quite aware that satellites are very important in weather prediction, but what exactly do we do with satellite pictures and satellite data is something that I will like to explain. Climate studies, because these days, we talk of climate so much that anything which happens in the weather, we have a kind of a tendency to relate it somehow to climate change. So we also should see what we can do with satellites about climate predictions, climate change, and climate studies. So from a little bit of history to a little bit of the future, and in between mostly about the present is the way in which I'm going to present this talk. As I said again, it's going to be a very simple talk. And at the end also, if there are any questions or comments, I'll love to have them. There is a picture here of an observatory in Chennai, which was there in 1796. While there is also a picture on the right-hand side about an INSAT satellite, the first in the series, INSAT 1A, which is dated 1982. What I'm trying to show here is that meteorology itself is a new science compared to classical science, but it's also satellite meteorology is a newer branch of meteorology. I mean, between the first rain observation in 1796 and the first satellite picture, which came in 1982, some 200 years have gone by. So this is a new branch of meteorology, and that's why we should know more about it as much as we can. There is a slight difference between classical meteorology and satellite meteorology. When we talk of things like pressure, temperature, humidity, the science came first. I mean, even 2000 years back, meteorology was known as a science. For example, the poet Kalidas mentioned in his Meghdut something about the internal physics of clouds. So this was known. But the instruments came much later. While in satellite meteorology, the instruments came first, the technology came first, and science followed. So this is a big difference why we should study satellite meteorology from a very different angle. It's a technology-driven science. This is the main difference between satellite meteorology and other branches of meteorology. So it's good that we're having a course on this subject. What was that new technology which made a new branch of meteorology? The new technology was simple. It was the ability to put an artificial satellite in space. The Earth has a satellite, the natural one, which is the moon. But when people thought that they could put an artificial satellite in space, moving around the Earth, it could do many things. And the simplest thing they did was to put a television camera on board. In fact, the first weather satellite was TIROS-1, which was launched by the US in 1960. And the name was Tyros, in which the T stood for television. So you can imagine that you're watching a cricket match or a football match somewhere, and there's a live telecast. So what the live telecast is, there are some cameras there, and the satellite brings you the view into your own house. So what the Tyro satellite did was just put a TV camera on board. And as the satellite moved around the Earth, you got a live telecast of global weather. As simple as that. Just like a live telecast of a Wimbledon match, we had a live telecast of the weather. And that, presented the weather in such a different perspective that everything changed overnight. And that is how the whole new branch of satellite meteorology was born. But the TV camera was very shortly replaced by what is known as the scanner. And there came radiometers, which was scanning radiometers, which was a very new idea. So as the satellite moved in its orbit around the Earth, the scanner went on scanning the Earth. Now, this was something like in 1960s when the idea of scanner was totally new. Today, of course, scanners are everywhere. Like, for example, you're entering an office building and you have to scan your fingerprint. Put your finger on the scanner and then the computer will allow you or not allow you to enter the building. Or you buy something in the market and you want to make a digital payment. Your mobile you use to scan the QR code, and then you can transfer money from your bank to the seller. Or in your office, you want to scan a document. There's a machine for that, or you can use any equipment made for scanning, and you can get a digital copy of the document. So scanners are everywhere, but when they were brought on a satellite, it was an extremely new idea, and then it spread everywhere in different satellites. So when a satellite is scanning the Earth, what it does is from every piece of land, it gathers data in numbers. And it will store all this data as the scan is over. All the data is available in one place. But what the computer does is that for every data point, for every point on the Earth, which is scanned by the radiometer, is assigned a gray shade. The gray shade typically goes from 0 to 255. 0 is black and 255 is white. And in between, you are having something like 254 shades of gray. So if for a number we assign a gray shade, what we get is an image. So the same thing which was scanned by the radiometer on board a satellite and was recorded as pure digits now becomes a picture. And we love to see images. We want to see them on TV. We want to put them on the cover of a book, or we want to bring documents or publish pamphlets. We put pictures. You can't put data anywhere. So the first thing that we get is not an image, but a data. And that is converted to an image for our convenience and because we like to see images. Otherwise, the data can be used itself. So in the next few minutes, we'll be seeing how the images are used and how the data are used. Both have different applications. So this is a typical satellite image that you see. Now, what does the satellite see what we cannot see? It's very simple. I mean, sometimes you see a TV debate and there are three people talking and everybody gives there's one problem and everybody gives his viewpoint of the problem and his solution. So in life, different perspectives are there and different people see things from a different vantage point. They have different ideas over things. Exactly the same thing happens here. Like when a human being on Earth looks up to the sky and looks at the clouds, he or she basically sees the cloud base. But when, like for example, there's an astronaut in the International Space Station somewhere above, that astronaut will look at the same cloud from above. So the astronaut will see the cloud top. Same thing, even in an unmanned weather satellite, the satellite will see the cloud top and not the cloud base. So it's the same cloud, but two different vantage points from which we are looking at it. One is from the cloud base side, and one is above the cloud, which is the cloud top. So this is why a satellite sees something what the human eye cannot see. There is one more thing. There is something that a satellite sees what human eye cannot see, besides the perspective or the vantage point. It's about the colors. All of you have seen a rainbow sometime or the other. I saw one just yesterday. And the rainbow typically shows 7 colors: violet, indigo, blue, green, yellow, orange, and red. So these are the 7 colors of visible light that a human eye can see. But it's a part of a spectrum. It's a small part of a wide spectrum. And a satellite can see wavelengths which are smaller than the violet or the ultraviolet, and which are longer than the red, which are the infrared. So a satellite radiometer can see in many more wavelengths which a human eye is not in a position to decipher. Now, the electromagnetic spectrum is something that we are using in day-to-day life. It's not something from a scientific textbook. It's what we do in day-to-day life. For example, you want to tune into a radio station, some FM 104 or something like that. You are using radio waves, frequency modulated, amplitude AM and FM and so on. Now you go to your kitchen and you want to heat up something, you use the microwave oven. So this is something that we use every day. Cell phone, they're with us all the time, and we are using microwaves. This TV, you put a dish outside and you look at the satellite and you get your favorite TV channel. So we are using microwaves in day-to-day life. Infrared, older people, they want to heat up their knees for arthritis. They use infrared heating lamps. Visible, of course, we see it every day. All the time we are using our eyes to see the visible wavelengths. Ultraviolet, nowadays it's very fashionable to have sunscreens to protect our skins from ultraviolet radiation. X-rays are very common. You go to a hospital and the first thing the doctor does is to find out what is inside, whether your bones have been broken. Gamma rays are now being used by surgeons instead of the normal conventional knife. They're using gamma rays for very pinpointed, accurate surgery. So there are basically 2 types of radiation from the electromagnetic spectrum. The radiation which comes from the sun and which drives the atmosphere is the basic source. From the sun comes all our energy. The spectrum of the solar radiation, which is received at the top of the atmosphere, matches the emission of a black body having a surface temperature of about 5,700 K. A black body is something which receives everything that falls on it, all the energy that falls on it, and emits according to a certain law, which is called the Planck's law. We need not go into that. So this is called solar radiation, and it peaks at about 0.5 micron. A micron is 1/1,000,000th of a meter. So anything which comes from the sun has the maximum intensity at the wavelength of 0.5 microns. Now, whatever comes from the sun is either reflected by the cloud tops, reflected by the ground, or scattered by aerosols and gas molecules. Some of it is absorbed, some of it is re-emitted. And then finally, all that was received from the sun has to be sent back to space. And that happens at a black body temperature of 283 degrees K. And that peaks at about 10 microns. So basically, we have 2 classes of radiation, a solar radiation and a terrestrial radiation. So these 2 distinct groups of radiation wavelengths is something that we deal with it when we deal with satellites. Besides that, we have to also decide in what orbit a satellite moves around the Earth. So there are various ways of rotating around the Earth. One is called a polar orbit. Most satellites are in the polar orbit. remote sensing satellites, and so on. And there is a geostationary orbit. Satellites like INSAT 3D are in a geostationary orbit, and they all offer different vantage points. And in between, you have a tropical orbit. We had a satellite named Megatropics, which was in the tropical orbit. So these are the different types of orbits so that we can look at the Earth from a different vantage point. Let's look at these three orbits in a slightly detailed way. So a polar orbit, as the name goes, is something that views the poles, the polar regions, every now and then. I mean, every time it makes one revolution around the Earth, it sees the poles. But what is happening is that underneath this orbit, the Earth is rotating around its own axis. So every time the satellite comes back to the equator, the Earth has moved a little, and you see a little bit of a different area of the Earth. So eventually, after a period of time, a global picture emerges. And then you can, even with one satellite, you can see the whole world, but not at one time. It's all different times, pictures combined together that you can get an idea of the whole globe. So this is a polar orbit. Then there is a geostationary orbit, like INSAT. Now, a satellite which is rotating at a height of 36,000 kilometers over the Earth has a very peculiar piece of attitude, I should say, because it looks from above to the Earth always at the same place. Something like what you have a CCTV somewhere, there's a camera which is looking at the same place all the time and telling you what is happening. So this is something like a CCTV type of radiometer far high in space at a height of 36,000 kilometers. And although it is moving in an orbit around the Earth itself is rotating around itself at a speed which matches the satellite. So because both are matching the speed, the satellite appears to be stationary at one place. But this can happen only on the equator. So we get a continuous Earth view from something like 60 degrees north to 60 degrees south, and the polar regions are not seen. So if you want to see the poles, then you have to have a polar satellite. If you want to see the non-polar area, you need a geostationary orbit. So eventually you need something like a few geostations, like 5 or 6, are needed to complete the global picture. So on the one hand, we have satellite which is called polar and satellite which are stationary. These are the two basic types of satellite that we need to observe the Earth. One thing in life is you never get anything which is absolutely perfect. Most situations in life are compromise situations. You have to accept this or that. You don't get everything that you want. And the same thing, particularly in satellite meteorology. You get something here and you get something there, but you don't get everything that you want. For example, take the wavelength. See, if you have a radiometer which is more sensitive to visible wavelength, you'll see the visible picture. If you have a wavelength radiometer which is more sensitive to water vapor bands, you'll see the water vapor channel. But you can't see everything with one sensor. Same thing with resolution. The resolution of a satellite is something that decides how clearly you can see. For example, when one's eyesight is not good, you put on the lens and then you see things clearly. So in the same way, the resolution of the sensor decides how clearly you can see. Then there's a question of ground coverage. If your satellite is far away, you see much more of an area. If your satellite is closer, you see lesser of an area. And there's a question of repeativity. How often can you look at the Earth? Because after all, we want to have a continuous. So if you're looking at the same place again and again, you don't see other things at the same time. So it is something like reading a book. I mean, if you just concentrate on one particular page, you won't read the other pages. Or on a page, if you're concentrating on a particular word, you won't have time to read the other. So it's like skipping a book where you're reading. So in a satellite, the wavelength of the sensor decides what you can see. The resolution decides how clearly you can see. The ground coverage is decided by the satellite altitude, how much area you can see. And the repeativity, the orbit decides how often you can see. So usually you can't get all of these four things to a degree of perfection. You have to compromise on something. And that's why we need so many satellites. Then we come to interpreting satellite images. I mean, when you see something on a satellite picture, you can just, kind of at a glance, just as you look at any picture, for example, which comes on WhatsApp or anything, there are some things which catch your eye. Some things are in the background and some things you're not bothered about. So when you look at a satellite image, you see some elements. These are clouds of different types. Then there are some patterns which catch your eye. For example, a cyclone. You know what a cyclone looks like now. Then there are in situ developments like a thunderstorm. Thunderstorms will grow vertically. They won't move from one place to another. They grow in the same place vertically, or they dissipate in the same place. And then there is a movement that we see in satellite, especially if you see a sequence of satellite pictures. You can see the monsoon evolving. You can see western disturbances moving across your country. So one should never look at a single satellite image. We should look at a sequence images. We should also know at what time the image was taken, by what kind of satellite was it. So we should look at an image with all kinds of information that we should have about the image, and then we should look at the image and try to interpret it. So satellite images, in fact, have several characteristics. First is the brightness. I mean, any picture that you see even in a newspaper, the brightest thing will catch your attention. So in the same way, when you look at a satellite picture, the brighter clouds will obviously grab your attention, and they are related to the depth of the cloud, the thickness of the cloud, the composition of the cloud. Then there is texture. I mean, some of us who go to a shop, for example, to buy some clothing for us, we don't look at the cloth. We try to feel it with our fingers. Is it soft? Is it silky? Is it rough? In the same way, there are satellite elements, picture elements, which are smooth. Some of them are fibrous. Some are opaque. Some are mottled. So that is what is called the texture of the elements. Then the form of the elements. The elements may be regular, they could be circular, or they could be irregular. Then there is a pattern associated with the elements. It may be associated with the topography, with the mountains, like there are some features which are on the lee side, some features are on the wind side. Size of the pattern, some of them are very large and some of them are very small. Then there's also vertical structure. Like, for example, some of the taller clouds will, and if there is sunshine, the taller clouds will throw a shadow on the lower cloud. So from that, you can find out which cloud was taller and which was shorter. So there are many characteristics which we have to look for when we are actually looking at any satellite picture. There are some more features. Many times you see long bands in satellite picture. Some of them are pretty long. They go from one continent to another. Then there are circular bands or spiral bands, like you see in a tropical cyclone. Then there are comma-shaped clouds, or there are crescent-shaped clouds, which you see in the extratropics usually. And there are curved bands and linear bands. So these kind of features, which are large-scale features, they are generated by large-scale clouds, and we should look at them to find out what is happening, not to the local weather, but to general atmospheric circulation. So some of these bands are so long and their length is much larger than the width. Some of them are associated with jet streams or the lee waves. Then there are cellular features, like some of the cumulus clouds come as round filled up cells, while the stratocumulus clouds come as open cells. Then there are stratiform features like clouds which spread over a huge area, like in a winter situation, you see fog. And fog will cover, for example, if you look at North India in the month of December or January, there'll be extensive fog from Himachal Pradesh to Arunachal Pradesh all along in the satellite picture. So these are the characteristics that we look for when we try to interpret a satellite image. Now this is a table, not exactly for any particular study, but it just tells you what we have these days in our own INSAT 3D satellite. And this satellite has 6 channels. As I said, the radiometer sees in different wavelength regions, and a visible region covers 0.55 to 0.75 microns. The shortwave IR covers in 1.55 to 1.7 microns. The midwave IR ranges from 3.8 to 4 microns. Then we have the water vapor absorption band, 6.5 to 7.1 microns. We have 2 thermal infrared bands, 10.3 to 11.3 and 11.5 to 12.5. So we have around 6 channel imager on the 3D satellite that we have today. The resolutions are different. The visible picture is the sharpest. It has the resolution of 1 kilometer, so you can see small clouds. The infrared channels have 4 kilometers resolution, so we can see slightly smaller cloud, but not very small. And the water vapor channel is 8 kilometers, because basically what we see is the water vapor amount in the atmosphere. So these are the resolutions ranging from 1 to 4 to 8 kilometers in the present INSAT 3D imager that we have. Okay, this was a recently taken picture of the monsoon situation that we have. And we have a visible channel picture, which is on the left-hand side. You can see that half of it is dark and half of it is lighted, illuminated. Then you have an infrared channel picture in the middle, which shows differentiations of gray and white. And we have a water vapor channel picture, which has very broad bands. There are a lot of black areas which are dry, and there are grayish areas which are slightly moist, and there are the white areas which are full of moisture, like clouds, for example. So you need to compare these 3 types of images, and then from all 3 put together, you get an idea of what the atmosphere is doing at that particular moment. So you should know what you're looking at and what you're looking for, and then you get an idea. This is a visible channel picture taken recently, and you can see the monsoon active over central India, also over the Himalayan foothills. And the first thing you can see is that the ocean is black, because in the visible channel, the ocean absorbs the energy and doesn't reflect much. So it appears black. While the land is gray, you can see the shape of the Arabian Peninsula. It's in the grayish color. Then there are various clouds which are very tall, and therefore they appear white. They are thick and tall. And then there are shallow clouds which are gray. So from a visual channel picture, we can find out a little bit about the depth of the clouds, where the convection is active, which part of the land is not having clouds over them, and the state of the seas. All of these things can be interpreted from the visible channel. The same scene, when you look in the infrared, you'll see that this is an afternoon image, that the land is hot and therefore it is black, while relatively the ocean has not warmed up that much. So the ocean appears gray. Even land appears gray. I mean, there's not much of distinction in the temperature of the ocean and the land. The tall clouds again appear white because they are cool. They have risen high and the temperature is low. So in an infrared channel picture, we see clouds which are white, meaning that they are very tall, or they could be cirrus clouds which are at that height. We can see that the land is very hot in the afternoon and the sea is relatively cooler. So such features we can find out from an infrared channel image. And then the same scene in water vapor, the resolution is 8 kilometers, much coarse compared to the other channels. And you can see that the whole picture is fuzzy. You can't distinguish between the boundaries of land and ocean, because it is neither looking at land nor it is looking at ocean. It is looking at the moisture. So it is the Black areas are those which have no moisture at all. You can see that to the northwest of Rajasthan, where the monsoon has not reached. So that is kind of blackish, and you can see everything else is gray because it's a monsoon area, and that has covered that gray region, while the white ones are mostly clouds which are risen very high. So in this way, you can derive different pieces of information by looking at different channels of the satellite. This is one picture taken on 19 July, just last month, and it's an afternoon picture. And the one on the left is the visible channel picture, the one in the middle is an IR channel picture. Now, what you can see by comparison is that there are some pieces of cloud which are white in both visible and IR. These are thunderstorms because they are thick, they are very tall, so they are cooler at the top and they are thicker in depth, and they grow usually there at the same place. So you can immediately mark them out, these white spots, as thunderstorms. So this is for the afternoon. This is a typical cyclone picture. And this was a picture of the cyclone Nisarga in 2020, which was crossing the west coast just at that time, 3rd of June 2020. And you can see typically it's like a perfect picture of a cyclone. You see them on TV, you see them in newspapers. And there's a certain distinct pattern. There is a central dense overcast, then there is an eye of the cyclone right in the center, and there are spiral bands. So if you look at a picture like this, you can at once tell that this is a tropical cyclone. And then you can see movement. This is a rather older sequence of this from 2016, January 2nd to 5th. It's a sequence. And you can see the western disturbance, which originates over the Mediterranean Sea and comes from there in sequence crossing Afghanistan, Iran, Iraq, Pakistan, and so on, and then comes into our territory, moving slowly over several days. And you can see the kind of comma-shaped cloud that it has. And then it passes off and the sky is clear. So in this way, if you have the same region, looking at the same spot in the same region, you can see clouds moving, and then we can accordingly predict the weather very well, that this is what is going to happen tomorrow, this is going to happen day after tomorrow, and so on. This is a picture of a pre-monsoon situation. It's a water vapor image, and you can see the black spots where there is no moisture or the monsoon has not shown any precursors. Well, in the center of the picture, you see a long gray band and a lot of white spots, something like what's called the ITCZ, or the Intertropical Convergence Zone. And you can actually see from this, it's a picture taken on 18th May 2017. 18th May is a little before the monsoon advanced into the country. And you can see that the monsoon is literally knocking at Kerala's door. So this is what you can get at a glance, what the monsoon is doing. And then you can say, well, the monsoon will arrive in the next few days or next 10 days and so on. So the water vapor images are extremely good for following the path of the monsoon. Then we come to quantitative product derivation. From the images, or from the data, there is a lot that we can derive besides looking at images. There are two different characteristics of the channels. The visible and the water vapor channels are not calibrated with respect to temperature or moisture. I mean, you can't say that if this pixel, a pixel is a picture element, if this pixel has this much of grayscale, it means this. You can't say that. While in an IR channel, the pixels are calibrated with respect to temperature. So if you see a grayscale in an infrared channel, we can say the temperature was this. So from an infrared channel, we can derive a lot of variable products. The upper level cloud motion winds, we can derive sea surface temperatures. We can derive temperature and humidity soundings, we can compute the outgoing long wave radiation, and we can get the large scale precipitation. So from an infrared channel, because it has calibration, we can derive a host of products. Not so with the visible and what vapor channel, but we can derive some cloud motion winds, which are in the low and middle level in a kind of a qualitative sense. So for most product that we derive from satellite is the infrared channel that is used. Then again, there's a problem with clouds. Sometimes we want clouds and sometimes we don't want clouds. So if the clouds are present, we can derive the cloud motion winds, we can derive the outgoing long wave radiation, and we can derive the large scale precipitation. If the clouds are absent, then we can derive sea surface temperature, we can derive outgoing long wave radiation, and we can retrieve the vertical temperature and humidity profiles. Of course, if there are no clouds, then we cannot get rain for obvious reasons. Let's look at the sea surface temperature. In the olden days, how was the sea surface temperature measured? Basically, they used to be measured in ships. And the ships used to go in a certain lane. I mean, no one was wandering around. There were ships for doing business between countries. There would be import and export of products. So they had shipping lanes attached for them, and they used to move only around those lanes. So a large part of the ocean was unobserved because nobody went there. Then came moored buoys and drifting buoys and floats. So we now have information from various other instruments. So when the ships were there, it was a very restricted area that we saw. But satellites cover the whole globe, and that's why we can now do satellite retrievals for almost the entire area that is covered by the sea. It's rather easy to find out because we are measuring the temperature of the radiation that goes, we are measuring the radiation that reaches the satellite, and we convert it back to the temperature by applying Stephen Boltzmann law, which says the radiation is proportional to the fourth power of temperature. So we can get back the sea surface temperature from the satellite radiance, which is relatively simple, but not quite. There are many problems. For example, when you are measuring sea surface temperature from a ship, what is done is that there is a sailor standing on the deck, the edge of the deck, and he lowers a bucket with a rope. Like, you pull up water from a well, and then he lowers the bucket into the sea. It goes something like a meter below the surface, and then he pulls back the bucket to the deck and puts a thermometer in it and says this is the sea surface temperature. But with a satellite, it is different. The satellite, just the outer membrane of the sea, or the outermost small cover called the skin, that radiates, and that is what is measured by the satellite. So you get a skin acid. So they're not exactly the same. Then again, if there is a clear sky, the satellite can look at the sea surface. If there is something like a little bit of cloud, well, you're looking at the cloud, and you're not looking at the sea. So there is a possibility of a cloud contamination. Sometimes what happens is that the intervening atmosphere between the surface and the satellite may scatter some radiation, may absorb some radiation. So these are the errors, like contamination errors, attenuation errors, which have to be kind of accounted for. And for that, we use multi-channel or a split window. That's why you saw the thermal infrared window was 10.3 to something and 11.5 to something. So we split the channels and apply these corrections. But after having done all that, you get a good picture. This is a picture taken on 14th July 2023, and you can actually, when everybody was talking of El Nino, you can actually see the El Nino. El Nino is the difference of the sea surface temperature from the normal, and the brown areas are the warmest. So you can see this a little bit of circular outline there to the west of the coast of Peru in South America. And the temperatures start warming up from there, and then they go, the warming builds up to the west, and then India is in trouble. So the SST monitoring is extremely helpful. Of course, we have still additional ships, buoys, and floats, but the main data comes from the satellites. And that's why we need a global picture to tell how the ocean is affecting the atmosphere, how the El Nino and other situations are going to bother us. Come to cloud motion winds now. It is rather simple to find out winds from a satellite image. You can see the image on the left-hand side, which we have spotted a cloud at a place A. And we spot the cloud and try to look for the same cloud in a successive image taken, say, half an hour later. You can do that with a geostationary satellite because you're looking at the same scene all the time. And then you find that the same cloud has gone from place A to place B in half an hour. So you measure the distance, divide it by 30 minutes time, and you have the wind. So we use clouds as tracers, and we use patterns as tracers, and then divide by the time taken, and you can estimate the wind at that level. Basically, a very simple thing to do. But in practice, there are lots of problems. For example, within half an hour, any single cloud is likely to change its shape. And then after half an hour, you find it difficult to find out where it has gone. Sometimes a cloud may gain height, or sometimes it may descend. And sometimes all clouds may look alike. So you can't even pick one out of them. All of them are looking alike. So a lot of quality control is required to eliminate spurious winds. And many times a huge number of winds have to be thrown out. Then again, at what height do you assign this wind? Because when you have a radio wind ascent, you get measurements from so many hectopascals, 850 or 700 and so on. It doesn't happen with cloud because they are not necessarily at your standard levels. They could be anywhere randomly. So you have to assign these winds at certain selected levels so they can be plotted on a chart. So these are the problems that you have with cloud motion wind, but still you use them. Now this is a picture taken in the monsoon situation very recently, 20th of July. And if you see the region to the northwest of India, mostly westerly winds, mostly. And they are in the region of the extratropics. And for the same day, if you look at India, over India and Indian Ocean, winds are mostly from the east. That's the easterly jet that develops during the monsoon season. So you get a lot of winds where there are no observatories at all. And you can plot them in your charts and you can see what is the field. Third is an important thing, what is called the outgoing long wave radiation. This is a very important component of the Earth atmosphere radiation budget because, as I said, the solar radiation comes from the sun and the terrestrial radiation goes out from the Earth. Now, these two have to balance each other. If they don't balance, then we have global warming. If there's more radiation accumulating in the Earth atmosphere system, the temperature will go up, as is happening now. So an outgoing long wave radiation, which is a broadband phenomenon, is something that we need to measure regularly to find out what is happening to the Earth and the atmosphere in terms of radiation budget. So this can be estimated from satellite because we have the infrared window. And again, we apply the same Stephen Boltzmann law and find out what was actually going into the satellite from the Earth and what is going to space. So statistically, what we do is we plot a regression between the satellite radiance measured by the radiometer and the OLR. And what we do is this. You take a long band stretching from 4 microns to 80 microns. This is what is the OLR. And what we measure is a small piece of it stretching from 10 to 12 microns. So this is statistically valid, but physically it amounts to inferring the whole from the part. But anyway, it works and it's used almost regularly, and we get maps like this. This is a map dated 12th of July 2023. And from this map, you can see that the blue areas are where the OLR was small, less than 240. That's our monsoon region where it is raining on 12th of July. And then there are the brown areas like the Sahara Desert where it never rains. So this is how we can get maps of global maps of outgoing long wave radiation, and without a satellite, I think we can never do such a thing. Next, we come to precipitation. On the land, we have rain gauges to measure rainfall. There are thousands of them all over the world, and we can make maps. But on the oceans, it's very difficult to put rain gauges. You just can't do that. And even on ships, you hardly find rain gauges because they're tossing and turning in the waves. So we come back to satellites. And what we do is that if the OLR is less than 240 watts per meter square, then we call it a rainy region. Then we also, so this is statistics again, but we also have in the microwave channel. See, the microwave channels are affected by radiation. For example, if you're watching a TV channel and all of a sudden you get a message that because it is raining somewhere, your TV channel signal is off. So in the same thing, if the microwave channel is attenuating the radiation, it means it is raining there. The third thing is to have a radar on board. See, these days you see pictures of Doppler radars where it is raining, where it is not raining. That is on land, and you can take a ground picture. But if you put a radar on a satellite, you can measure the precipitation between the satellite and the ground. So these are the three ways of getting precipitation from satellites. And this is again a global map of precipitation, which it would have been impossible to get without a satellite. And you can see this green and blue bands just to the north of the equator. And these are the places where it is raining. The date is June 2023 for that month. It's for the month as a whole. And you can see the blue and green areas where it has been raining pretty high. Now, this picture is taken from a US defense satellite, and it's called the Special Sensor Microwave Imager. So using microwave data, you can get pictures like this, especially on a climatological basis. A little bit about the microwave band, because we'll need it a few minutes later. So there are many bands in the microwave, like millimeter band, KO band, X band, C band, S band, L band. So they have different frequencies. For example, a C band microwave band is 4 to 8 centimeters, where an S band is 8 to 15 centimeters. So all of these bands are affected by different atmospheric processes. Like S band can cut through small clouds and see the bigger clouds. The C band is good for seeing clouds which are nearer to us. So in all of these things, finally the world settled down for what was called the Global Precipitation Measurement Mission. And this is a network of satellites. There is a single core observatory satellite, which is made by NASA and the Japanese Space Agency. And there are several research and operational satellites of different countries which make a constellation. So the core observatory was launched sometime in 2014 at an altitude of 400 kilometers. It covers the Earth from 65 south to 65 north. And the payloads capture the precipitation in there are two different instruments. One is the GPM microwave imager, and the other is dual frequency precipitation radar. This is a picture, which is kind of a computed picture, of course, of the rainfall on 20th of July, that's last month. And you can see the monsoon over India, the red and the pinkish spots, purple, red, and pink. Those are the heavy rainfall regions. And the rest are the greenish ones are the lower rainfall, and the pink ones are, of course, where there's no rain. So with this constellation of satellites, you can get a picture every couple of hours for the whole globe. And it is necessary because you want to know where it is. This is the GPM mission and its outputs. Difficult product derivation from satellites. See, previously we used to have balloons, we still have them. And the balloon, we tie an instrument to the balloon, and as it rises high in space, what is called the radio sound or the Raven sound, you get a signal that the pressure is this much, the wind is this much, the temperature is this much. So as the balloon flies high, say for an hour or so, we get a vertical profile of temperature, humidity, winds, and so on. But it's an expensive thing. I mean, balloons are consumables, and every time an instrument goes into the atmosphere, it's broken down and falls somewhere. So it's a problem of money. It's also a problem of location, because you can't do this over the oceans. You can do it only over the land. So there is a method by which we can retrieve the vertical temperature and humidity profiles from space. And what is done, the principle is this, that as Earth is radiating upwards, between what it is radiated upwards and what the satellite has measured, you can imagine that the atmosphere is made up of several layers. These are imaginary layers. And every layer receives something from below it and emits something to above it. So it's a constant give and take of radiation at every layer. And ultimately, what the satellite measures is just one value. Now, this is the problem, that from one value, you want to find out how the change has occurred from level to level. And it looks difficult, but it is possible. So we do this retrieval by having what is called a sounder. We assume that there are no clouds. We assume that there is no scattering. It has the vertical geometry has to be there, and the Earth's surface, we assume it's a perfect black body. But then we can retrieve the temperature and humidity at different levels in the atmosphere by breaking the radiation measured at satellite level into smaller pieces. And this is done with a sounder. INSAT 3D has a 19 channel sounder. There are 6 channels in the shortwave IR, 5 in the midwave IR, and 7 in the longwave IR, thermal IR. This also weren't visible. So when you have something like 19 channels, you can use the radiation measured by the satellite to get the vertical profiles, and it's global. So this is an extraordinary piece of information that you get from satellites. So let's kind of summarize what are the things that satellite can do for weather prediction. The weather satellites have many advantages. First of all, you don't have to collect data, you don't have to plot anything, you don't have to analyze anything. Everything is at a glance, all products, all images at a glance. And there are many, many places where we just don't get conventional observation: oceans, deserts, mountains, places where people don't live. So in all these places, we have satellite data available. So this is something which is a great advantage. At the same time, there are problems, like satellite products take time to be generated. They may take a couple of hours. They may also have errors in them, like the winds have errors of height assignment. The SSTs are skin temperatures. SSTs have contamination errors. The rainfall estimates have logarithmic issues. So then again, what has happened is that people have gone back to the basic data, the basic radiance. Instead of using the products, people are just assimilating the basic from a satellite into the NWP models. Now, this is a huge amount of data. For example, if you take an INSAT picture, it has something like 6,000 by 6,000 pixels, 36 millions in every channel of every image. So you can imagine that numbers of data that you're trying to assimilate from us, and then it comes every hour or every half hour. So it wasn't possible previously, but now that because the computing power has gone up so much, this can be done. And one of the successes of NWP models, it lies in the fact that they are now assimilating satellite radiances, not the products, but the radiance. So this has made a big jump in the performance of the forecast, I think, which we should understand. And this is not being popularized much. So what's the current scene in meteorological satellite? There are currently 27 operational meteorological satellites, quite a large number. The US has 10 satellites, 5 geostationary and 5 polar orbiting. China has 6, 3 geostationary and 3 polar orbiting. Other countries have 3, 2, and 1, and India has 2, some other countries have. So out of a total of 16 geostationary satellites, India has 2, And out of 11 polar orbiting satellites, India has none. We don't have polar orbiting satellite. We have, of course, for remote sensing, but not for the weather. We now come to climate applications quickly, and I think in 10 minutes I'll wind it up. So what has happened is over the last 50 or 60 years, a long series of satellite data are available. But when it comes to climate, the problem is that with every new satellite, instruments have improved. And with every new satellite, instruments have changed. With every new satellite, the orbit has changed. So because of this, the data is incompatible over the years. And it is difficult to construct long data series. But again, satellites are the only source of data over a large area of the world. So we have to compromise with the problem and use them in a long-term mode. But there are several specialized missions for climate. There's the GPM, which we saw. There is a scatterometer to get surface winds. For example, in a tropical cyclone, we would like to know what are the winds at the sea level. There's a satellite for carbon dioxide measurements, for ozone, for sea level. We have our own OceanSat for ocean parameters, and then there are projects for tropical storms and NISAR. We'll come back to that. So in the next few minutes, I'll try to quickly go through these things. Nowadays, carbon dioxide is the most important gas in the world. Everything depends on how much carbon dioxide is being added to the global atmosphere. And there's only one measurement place in Hawaii from where the CO2 measurements are publicized. But there is a satellite called the OCO2, the Orbiting Carbon Observatory. It's a NASA satellite, and it tries to measure carbon dioxide in different places of the world. So we can identify the sources and the sinks. There's another satellite, which is the US European satellite mission, which is called the Ocean Surface Topography Mission. In case the ocean circulation patterns, it has an altimeter. You know, altimeter is when you're flying on an aircraft, the pilot announces that we are flying at, say, 38,000 feet. How does he do that? He has an altimeter. So an altimeter sends a signal to the surface of the Earth, and the time taken to return to the satellite will tell where is the sea level. And you can, with a sea level altimeter, we can measure the sea level with an accuracy of 3 centimeters. So it's an extremely accurate instrument. And ozone is something very interesting ever since we discovered the ozone hole. And there are 2 satellites. One is the GOM-2, which is it's an instrument on METOP, and there's another instrument on NOAA-20. So they measure the ultraviolet radiation, and you can see this picture. The blue region is the ozone hole, and then we can find if the ozone hole is expanding or shrinking or whatever it is. OceanSat-3 was our own satellite launched last year. It has an ocean color monitor, an SST monitor, and a scatterometer, which gives sea surface winds. It's an extremely useful satellite of our own. Tropics is again a constellation of satellites, but these are extremely small satellites. You can imagine the dimension of a satellite is 10 centimeters by 10 centimeters by 36. You can hold it in your hand. The weight is just as light as 5 kgs. So when you have a constellation of such small satellites, launching them is so easy. And there are 2 already in orbit, while 4 more are in the planning stage. And these are low-level satellites, 550 kilometers altitude, low inclination for the tropics. And they will give you almost an hourly view of tropical cyclones with a resolution of something like 27 kilometers and 17 kilometers for precipitation. So you can cut through a tropical cyclone once every hour. So when that becomes operational, we'll get an excellent view of that. PACE is another NASA mission scheduled for next year. It measures the ocean color, but the name PACE stands for Plankton, Aerosol, Cloud, Ocean Ecosystem. All of them are related to each other, and all of them are important for climate change. So if you can measure these things on a continuous basis, that will be extremely useful. Then we have Sentinel. It's another satellite series to be launched next year. It's a European satellite series. Again, sea surface height, wave height, wind speed, sea ice. So everything about the ocean we are trying to monitor. NISAR is something I'd like to dwell for a minute. And NISA stands for NASA ISRO Synthetic Aperture Radar. This is ready almost. You can, if you go to YouTube, you can find a video on this. And it is to be launched from Sriharikota next January. This will be a near polar sun synchronous orbit with a return period of 12 days. It has two radars, an L-band radar and an S-band radar. And it will produce images of the Earth's surface with a resolution of 1 centimeter. You can imagine, I mean, 1 centimeter change in the Earth's surface can be seen so accurately. So this is something, it's a fantastic idea to measure changes in the Earth's surface with 1 centimeter accuracy. And the applications are enormous. You can watch the melting of glaciers. You can see the sea level rise because we have the coastal line of something like 7,000 kilometers. It can measure the groundwater levels. It can view the changing ecosystem. And even it can give an inkling into earthquakes and volcanoes, because that is something that for which no information is available online. So coming back to almost to the end of my talk, and I said we'll look into the future. We have looked into the future, and one can say that satellites have become indispensable for weather forecasting and climate studies. They give us global coverage. They give us information that no other source provides. And most of the operational satellites have backups. INSAT 3D has a backup. If something goes wrong with one, the other is ready for use. They have successor satellites backed up. And many new missions are coming up for climate, which are quite difficult to maintain, but they are being put up. And there's a lot more to be done. So to end this talk on the fundamentals of satellite meteorology, what I would say is that this 5-day training course is an extremely good idea. And I wish it all success. And I hope that in the next 5 days of your discussions, I think some new ideas should come up. So thank you so much for inviting me here for this talk, and I hope it's of some use to you. Thank you very much.